Hello and welcome to CMOS RF integrated circuits. Today we have started module 7. Actually we started in the last class little bit. We are going to talk about various noise sources, sampled noise onto a capacitor and noise that we see in a MOS device. So, in the last class we had just about started this discussion. We saw that if we have a resistor R, this is a source of noise and it can be modeled as a noiseless resistor R in series with a noise voltage. This noise voltage has a mean squared noise voltage of 4 kT times R times df, where df is the bandwidth over which we are looking at, frequency bandwidth. So, here K is the Boltzmann's constant, T is the absolute temperature in kelvins, R is the resistance of the device and df is the bandwidth. Now, we figured out where this noise is coming from. The origin of the noise is the fact that while the resistor is full of electrons that can move, these electrons are vibrating because of temperature. They are thermally excited. As you excite them more and more, the electrons vibrate more and more. As a result, now these electrons are vibrating over a resistance R. So, as they are vibrating more and more over this resistance R, they are creating a larger and larger voltage, right. So, this is what we observed. I mean, this is the mechanism by which the noise is produced. Fine, and I referred you to the work of Nyquist, Harry Nyquist, done way back in 1929 or 1930, in which he proved this result. Okay. Now, you can also do Thevenin to Norton equivalent transformation, and the same resistance R can now be re-represented as a noiseless resistance R in shunt with a current source. So, this is a current source which has a mean squared noise current that is equal to 4 kT times df divided by R. Okay, this also we inferred from the previous result in the last class, right. Then what we did was we put two resistors, let us say R1 and R2 in series. Now, when you put R1 and R2 in series, it is natural to combine the two into one combined resistance R1 plus R2. This is what you would like to do. Now, does this work in terms of noise as well? So, R1 and R2 in series, that is basically noiseless R1 in series with a voltage source and then noiseless R2 in series with a voltage source. Now, the contribution of the first voltage source is 4 kT R1 df, that is Vn squared, Vn1 squared, and Vn2 squared mean squared is 4 kT R2 delta f df. Okay. And when you add these two voltages, what is going to happen? This can be represented as noiseless R1 plus R2 in series with a voltage source, which is the sum of the two earlier voltage sources. Now, the earlier two voltage sources were not really voltage sources, they were in terms of the square of the value, right. So, the combined value, we showed that since these two voltage sources in the mean squared sense are uncorrelated with respect to each other. They are random processes uncorrelated to each other. So, therefore, the square of the sum is equal to the sum of the squares. So, what I was trying to say in the last class, but I think we were really short on time, is that if I take V n 1 and V n 2, then the total mean squared of V n 1 plus V n 2 is the sum of mean squared of V n 1, V n 1 squared, mean of that, V n 2 squared, mean of that, plus twice the cross correlation of V n 1 and V n 2. Now, since these two noise sources are mutually independent of each other, they are random processes that do not have any bearing with each other. So, therefore, the cross correlation of V n 1 and V n 2 is going to be equal to 0, and therefore, this entire term is not going to come into the picture, which means that the sum of the two, mean squared of the sum of the two, is equal to V n 1 squared plus V n 2 squared. What this means is that now I can model this as 4 k T R 1 d f plus 4 k T R 2 d f, which is equal to 4 k T R 1 plus R 2 d f. And that fits perfectly well with my intuitive answer that if I put two resistors in series R 1 and R 2, then the combination of the two should be equal to R 1 plus R 2. In terms of noise, these are also, this statement is also true in terms of noise. Okay. So, the next thing that we have to work on is two resistors in parallel. So, if I have got two resistors R 1 and R 2 in parallel, okay, I will replace these two resistors R 1 and R 2 by resistors in series with noise voltages. I know the values of V n 1 squared and V n 2 squared, means of these two I know. Now, unfortunately, this is a difficult problem to solve, but life will be easier if I do the Thevenin to Norton equivalent transformation, in which case I am going to have a current source in parallel to the resistor. Right. Now, when I have two currents in shunt, I can combine the two currents, I can add them up, right. So, if I have I n 1 and I n 2 in shunt with each other, then I can combine them to be one current source, which is of value I n 1 plus I n 2. Now, so I n 1 plus I n 2 squared, mean of that is equal to the same mathematics as before, I n 1 squared plus I n 2 squared plus 2 I n 1 I n 2 combined mean of everything, which is equal to I n 1 squared mean of that plus I n 2 squared mean of that plus twice times I n 1 I n 2 mean of this. Now, the first term I n 1 squared, we know what it is. Second term I n 2 squared, we know what it is. The third term I n 1 I n 2, mean of that is 0, because I n 1 and I n 2 are two independent random processes, they have nothing to do with each other. So, the cross correlation of I n 1 and I n 2 is equal to 0. Okay. So, this third term is equal to 0, which means that I have got two current sources in parallel, both one has RMS of I n, one has mean squared of I n 1 squared, second one has mean square of I n 2 squared. They are independent with each other, with respect to each other. Then the sum of these two currents will have a mean squared, which is equal to the sum of the two individual mean squared noises. So, what that means is the following, that R 1 noisy, R 2 noisy combined can be equivalently represented as R 1 noiseless in shunt with R 2 noiseless in shunt with a current source which has a mean squared current that is equal to I n 1 squared plus I n 2 squared mean of each, which is equal to 4 k T d f by R 1 plus 4 k T d f by R 2. Right? This is the story so far. Now, of course, I can combine the two resistors to be one of value R 1 R 2 by R 1 plus R 2, right. And if I do so, then I can also transform this current source into its Thevenin equivalent. So, if I transform this current source into its Thevenin equivalent, then what I am going to get is this resistance R 1 R 2 by R 1 plus R 2 in series with a voltage source, where V n squared is equal to I n squared times the square of the resistance. All right. Now, I hope you have figured out by now that 1 by R 1 plus 1 by R 2 is really equal to R 1 plus R 2 by R 1 R 2, right. So, this is going to give me 4 k T d f times R 1 R 2 by R 1 plus R 2, which is the result that you expect. So, if you lump the two resistors together R 1 and R 2 combine to form a new resistance R 1 R 2 by R 1 plus R 2, then the noise of the new resistance is, surprise surprise, 4 k T times R 1 R 2 by R 1 plus R 2 times d f, right. So, if you put two resistors in parallel, then In terms of resistance value, you get R1 parallel R2. In terms of noise, you get the noise contribution of R1 parallel R2. You do not have to work with R1 and R2 individually. So, this is nice. So, series and parallel combination of resistors works. The problem is that once you move beyond resistors, nothing is nice anymore. All right. So, once you have capacitors, inductors, etc., life becomes miserable, probably. So, what we are going to do now, next step, we are going to examine an RC network. All right. Now, the RC network, the resistor is the only thing that is noisy, the capacitor is noiseless, right. Now, the question that I would like to ask you is as follows. Suppose you have got an RC network and suppose you apply the input across the RC and you take the output just across the C. What noise will you see at the output? This is the question. All right. So, to do this, we have to replace the resistor with its equivalent model, which has a noiseless resistor and the noise voltage source, and then we have to work our way. So, let us see what can be done. So, we are going to replace the resistor with noiseless resistor in series with a voltage source. This voltage source has a mean squared noise voltage of 4 kT df times R. All right. Let us say that I can apply my input, I will see some output. Then what I am going to do is I am going to null the input, I am going to use superposition basically, null the input, apply the noise, see what noise comes out at the output. The result will be the sum of these two, right. So, for purposes of noise, we can as well consider that the input is equal to 0, because we are going to do superposition as far as the noise is concerned. So, let me connect the input to 0 volts, all right, and I need to find out what is the voltage across the capacitor. That is going to give me the output. So, I have got a voltage source, let me move the voltage source to the other side. To make life easier. Right. This is what I have got and I want to find out what is the voltage across the capacitor. So, if I apply a voltage V over here instead of Vn squared, let us say I apply Vn. If I apply Vn, then what is the voltage that I see across the capacitor? I see the voltage across the capacitor has a Laplace transform that is equal to Vn of S times R by 1 plus SCR. Am I right? Nope, I am not right. 1 by 1 plus SCR. This is correct. Okay. So, the voltage across the capacitor has a Laplace transform that is like this. Alright. Let us not write Laplace transform, let us convert it to j omega. Now, the next step for us is to take the magnitude of this. Alright, and Vn of j omega magnitude squared is what? Vn at j omega magnitude squared of it is really equal to 4 k T r times df. df can be translated in terms of d omega. How do you translate df? Right. So, this is what I have got over a little bit of bandwidth, over a small frequency d omega, small angular frequency d omega. If I look, I am going to get so much noise. Now, the noise at one frequency is not related to the noise at any other frequency, these are independent of each other. As a result, if I integrate the noise, if I want to find out the total noise, you really have to find out, you really have to take the noise voltage squared at each of these individual frequencies and add the total. That is how we are going to do it, right. So, the total noise voltage squared at the output noise voltage squared is equal to integral of 4 k T r by 2 pi divided by 1 plus omega squared r squared c squared times d omega. Going from what to what? Traveling from frequencies starting from 0 all the way to infinity. Okay. So, omega is going to range over this entire bandwidth. Now, we have to work on this integral. This integral is not actually not very difficult. Okay. And if you look up your table of integrals, then what you are going to find is that the integral d omega, I am sorry, integral dx by 1 plus x squared is equal to tan inverse of x. Okay, that is what you are going to find. All right. So, let us try to put that in that form. So, to put that in that form, I have to replace omega r c by x. So, if I make this substitution, then d omega will be dx by RC, and what that means is that this is what it means as far as we are concerned. And then I use my integral from wherever you have studied integration. All right. Now, as x tends to infinity, tan inverse of x is basically equal to pi by 2. X tends to 0, tan inverse of x is 0. All right. And now you do the simplification, and all of the 2's will go, pi will go, r will cancel out. All you are going to be left out with is k T over C. Surprise, surprise. What did we just do? What have we done over here? We started with a resistor and a capacitor. Before we started with a resistor and a capacitor, I gave you the entire story that where noise is coming from. The noise is coming from the resistor. All lossy elements are noisy. Lossless elements are also noiseless. So, the capacitor, which is not consuming any power, is also not going to contribute in terms of noise, right. So, we started from this story. This was our starting point, and we took a normal RC network. We put resistor, capacitor like I have drawn over here, and the question was how much noise do I see at the output. Now, when you talk about a resistor, the noise that you see over a given bandwidth df is 4 kT R times df. Okay. I am interested in finding out how much noise, right. This is some sort of an RC network, presumably it is a low pass structure, does not matter. At the output, I am going to see noise at all frequencies, and if I add up all the noise at all the different frequencies, that amounts to working this integral out, right. I work out this integral. The integral was not trivial, but not very difficult either, and I found out that the total noise, the total of all the noise that you see over all the frequencies, when you look at the mean squared noise voltage at the output of this RC network, then that is equal to kT by C. So, mystery number 1 is it is no longer proportional to R. Mystery number 2 is now it is inversely proportional to C. So, the resistor contributed the noise, the capacitor was noiseless. Now, the result is showing that if I make put a larger capacitor over there, I will get lesser noise. It has nothing to do with the resistor at all. What is going on? So, you are probably all confused, right. So, we started by saying that the resistor is noisy. Now, I am showing you that the total noise decreases for a low pass RC structure, the total noise decreases if I increase the value of the capacitor. What is the story? Next thing to observe is that there is no DF anymore, alright. Earlier the noise for a resistor over a given bandwidth is 4 kT R DF, that is the mean square noise voltage over a given bandwidth delta F. In our case, in this case, the noise voltage squared, the mean squared noise voltage at the output is over the entire range of all frequencies. We are no longer saying that let us restrict ourselves to this bandwidth. This over all frequencies, mean squared noise voltage is kT by C, period. It is a beautiful result, it is a classic result, and the conclusions can be enormous. So, there is no limit to what the value of that resistor is. The value of that resistor can be anything, it can be 0, it can be 1 ohm, it can be 100 ohms, it can be 1 giga ohm, it can be an open circuit, it can be tending to infinitely large number of ohms, 100 giga ohms. It does not matter, the integral is always equal to, the total noise is always equal to kT by C, right. So, it does not matter what the value of that resistor is, it may be there, it need not be there, it can be an open circuit, it can be an infinitely large resistor. I will still get the same value for the total noise voltage, mean squared noise voltage over the entire bandwidth, that is still going to be equal to kT by C. Okay. So, if you have a switch that sampling a voltage onto a capacitor, during the sample phase the switch is on, when the switch is on it looks like the RC network, right, and then suddenly you switch off the switch, you remove the switch, in which case the switch is now a resistor which is very large, that is also fine. The noise that is deposited on the capacitor is kT by C. The RMS value of the noise, not RMS, the mean squared value of the noise voltage that you have deposited onto the capacitor is kT by C. Okay. It is coming from the switch, but its value has nothing to do with the switch, the resistance of the switch, it is irrelevant. It is coming from the switch, true, but its final value is independent of the resistance of the switch, right. So, this is a very sweeping result. All you have to do is make your capacitor larger, the noise voltage that you will see is smaller, is going to be smaller. Now, before we jump too much with this kT over C business, how is this happening? What is going on over here? So, it is like this, when you look at the power spectral density of a noise voltage, it is uniform. Let us not draw it as a function of f, let us say it is a function of omega. If I draw the power spectral density of noise, then it is uniform, it has a value of 4 kT times R. This is the noise of a resistor. And then you say let us look at this band of width df d omega, because this was omega, right, in which case it is no longer 4 kT R, it is 4 kT R by 2 pi. No, 4 kT R by 2 pi. All right. So, this is the story that we have got as far as the resistor is concerned. Now, this noise is passing through a low pass filter, and the low pass filter has a cutoff frequency of 1 by RC, right. That is the fun part. Now, when you pass this noise through a low pass filter, what you get is this. This is what comes out of the filter, only this portion comes out of the filter. Earlier, if you had done the integration from 0 to infinity, you would have gotten infinitely large amounts of noise. But now, if you do an integration from 0 to infinity, it is going to be finite, right, because the tail has been removed, I mean it has been cut off. The filter cuts off high frequency noise, it is a low pass filter. All right. Now, if I integrate this noise, then I am going to get kT by C as the total mean squared noise voltage over all frequencies. All right. So, what you are really doing is you have got this 4 kT R by 2 pi, this is the power spectral density, but at the same time the cutoff frequency of this filter is 1 by RC, okay, and that is what is instrumental in removing the R from your expression. So, if you multiply 4 kT R by 2 pi times 1 by RC, that is the portion that is coming through, the remaining portion is not coming through. If you make that as a first order approximation, then what you end up with is R cancels with R and you get kT by C times 4 by 2 pi. Okay. It is close to the answer, but not exactly the answer, because you have not done the integration properly. You have just done a super approximate deal over here. You have said that only frequencies below 1 by RC pass through, frequencies above 1 by RC do not pass through. So, that is what you have said, and as a result you have got a little, you have got a wrong result over here. The proportionalities are still the same. So, this is what is wrong. Okay. You should be getting 1 over there, not 4 by 2 pi, 4 by 2 pi is less than 1, but the kT over C part is correct, and that is kind of giving you the intuitive feeling that the total noise is no longer going to be proportional to R, instead it is going to be inversely proportional to the value of C. Why? Because the cutoff frequency is 1 by RC. Okay. If I increase R, if I double the value of R, the cutoff frequency is going to go down by 2. So, lesser frequencies will pass through. Okay. So, the total noise I will see at the output is going to be lesser. All right. So, this is basically the idea. All right. Now, how are we going to do our analysis? If we have a lot of resistors, so suppose I have got a network which is full of resistors and capacitors, let us say inductors also, does not matter. Okay. Let us say the resistors are the noise sources, then all you have to do is you have to consider each noise source in its own merit. Okay. Find out what is the noise voltage because of each individual noise source, what is the mean squared noise voltage because of each individual noise source as a function of frequency, right. Add up all of these, add up all the individual, you are doing superposition of a lot of different sources, right. So, noise source number 1, what is the noise voltage at the output because of noise source number 1 as a function of frequency, mean squared noise voltage at the output, find that out. Do the same for noise source number 2, do the same for noise source number 3, right. Then you add everything up and then you integrate everything from 0 to infinitely large frequencies, that will give you the total mean squared noise voltage over all bandwidth, over all frequencies, right, for the network that you started with. So, let us just do a quick example. Let us say that this is what I have got R1, R2, R3, R4, I do not know what this is, but let us say this is what I have got, right. What are you going to do? You are going to first find out what is the contribution of R1. First of all, input is 0. Then you say you replace R1 with its equivalent noise model. You assume R1 is noisy, everything else is noiseless. You put your noise source over here, noise source has value of 4 kT R1 times df. Find out what is V n squared at the output because of that one noise source over there, right. It is going to go through the transfer function of the entire circuit. Then do it for resistor number 2, then do it for resistor number 3, and finally do it for resistance number 4. And then you have to integrate all of these, presumably you have already got df inside your expressions, you have to integrate all of these over all frequencies. Okay. That will give you the total mean squared noise voltage over all frequencies. Sometimes these frequencies blow up, these integrals blow up to infinitely large. In those cases, you have to restrict yourself and say that I will not go from 0 to infinity, because that will give me a bad result, right. It will tell me, it is basically going to tell me that I have infinitely large amounts of noise, right, and you will restrict yourselves to frequencies that you are interested in. So, typically that is what we do, right. So, I am going to end this part of the story over here and move on to the next part. The next part is noise in a MOSFET. So, if you think about noise in a MOSFET, what are the different sources of noise? So, first you make the gate oxide, then the poly on top of the gate oxide, then you implant the drain and the source. Okay. So, this is your MOSFET. Now, what can cause noise in a MOSFET? So, the first thing that comes to mind is the fact that the gate itself is made out of poly material. So, this gate is poly material and the poly material is really used to make resistors as well. So, that means that the gate is resistive. Okay. The gate is resistive and therefore, it is going to contribute noise. Agreed? All right. The gate is a distributed resistor. Right. If you have made a contact at the center, the gate is a distributed resistor. The charge is going to distribute yourself. Each part of the gate sees its own capacitance and charge develops all over the gate. So, it is really a distributed resistance. You can lump it into an equivalent series resistance with capacitance. You can lump it into that model, that will give you some noise. So, the gate will give you some gate noise. Fine. What else? What else can contribute to noise in a MOSFET? So, when you apply a voltage between gate and source, let us say source, drain, body, everything is connected to 0 volts. You apply a voltage between gate and 0 volts. So, gate is let us say at 5 volts, much above the threshold voltage. Then what is going to happen? A channel is going to develop. A channel is going to develop right beneath the oxide layer of the gate. So, right beneath the oxide layer on the surface, a channel is going to develop. Okay. First of all, the bulk of the MOSFET is going to get depleted of all the holes that were there. Now, considering that you have only lightly doped the bulk of the MOSFET, there were not too many holes to be depleted in the first place. That is fine, life is like that. So, there are these fixed charges over the bulk of the MOSFET. These are places where the holes have gone away from, right. Now, besides these fixed charges, right underneath the gate, layer of inversion is formed. Now, what do you do with this layer of inversion? What does it remind you of? What about these electrons? These electrons are moving because of temperature, they are vibrating, aren't they? It is exactly the same like a wire. You formed a wire. In a wire, the electrons are moving around because of temperature, because they have energy to move around. Okay. So, as long as they have energy to move around, they are going to move around. They are going to bounce against each other, etc., etc. And as these electrons move around, they are going to develop a potential. Okay. You could think of it that way. or you could convert it into the Norton model also and say that there is an additional noise current in shunt with the channel. Agreed? So, if this is a noisy MOSFET, okay, the model for a noisy MOSFET is, first of all, you have got some gate noise, okay, and then you have got the noiseless MOSFET, and in shunt with the channel of the noiseless MOSFET, there is